So what you're doing here is, we have taken a two mass spring damper system. Okay. The force is applied to, if you have to pay careful attention here, force is applied only to mass 1. Right? You see that force is not applied to mass 2. Force is being applied only to mass 1. This is displacement of mass 1. So again, what was the assumptions we made? Assumption is, except this, the masses of spring and damper are negligible.
As far as that equation goes, though, why did we have to go back and all of a sudden apply the Laplace?
Because we are going to, I told you right, we are going to, last class what did we do? We derived the equations of motions as a differential equation and then took the Laplace.
So that, but, right, so the Laplace though has nothing to do with this part.
This is Laplace. All this is Laplace. See, all this is Laplace, right? So what if you look at this f of t, this is what? This is a time-based equation, okay? This thing is time-based. This thing is what? Not universal. This is a Laplace. Frequency-based. So how do you get this? You just take, if you take the Laplace transform of this, you're going to get this. We are trying to directly express everything as Laplace. Got it? So we are saving one step for modeling the system dynamics. So how do we model system dynamics? What did we do? We looked at this. So if we were to just do modeling of dynamic modeling of this, you would go by evaluate the forces applied to mass 1, what is the displacement, what is the acceleration of mass 1, what is the acceleration of mass 2, what are the forces applied for mass 2. Got it? That is how you would do it. This is a direct method of coming up with the equations of motion in frequency domain is transfer function. Okay? What is the equations of motion again? Do you understand by equation? You understand what is the equation of motion? Have you come across this term, equations of motion?
Kinematic.
Motion. Equations of motion? No?
Yeah, I was thinking about kinematics.
Kinematics and kinetics, both. It's dynamics. Yes. Equations of motions are nothing but, what is the equation of motion? I told you what an equation of motion is. It's an input-output relationship of a system. The input-output relationship. When you do a differential equation, you are also deriving the input-output relationship. So here we are deriving the input-output relationship in terms of frequency domain. Okay? So let's continue with this. Are you guys following until now?
Yes.
If you do it enough number of times, you'll be able to understand. Z, are you following? Okay. So what you do is, now this, you have x2 of s equal to, what are the forces applied?
So,
Huh? F of s. Right. Got it? Now look at the second one. Mass 2 equation. Can you tell me what is mass 2? Mass 2 will be very similar, except it will be sum of impedances connected to N2, okay, minus into x2 of s minus sum of impedances common between M1 and M2 into x1 of s again sum of applied forces to M2. Okay. So what are some of impulses connected to M2, tell me? It is K2 plus K3 FV2S FV3S plus Q2S square. This whole thing into X2 of S minus, this will remain the same, K2 plus FV3S into X1 of S is equal to 0. You understand why this is 0?
There's no force.
There's no force. There's no force applied to mass. Okay. Now, when you combine these two, you think about this. Equations of motion are let me write this. M1 square plus F1 F3 this M1
The one you're writing down, that's both equations.
both equations together. Okay. So these are the equations of motion. What is the input here?
0.
What is the input?
Inputs.
Input is f of s.
Oh, wait.
What is output is?
Excellent.
It's either x1 of s or it could be x2 of s. There are two outputs here. They are not necessarily the same. Got it? So this, what I've done here is, so look at these two equations and think about simultaneous equations. Do these look like simultaneous equations? What are the variables here?
Same variables.
What variable? What's same?
Yeah. FV3 S. That's not the same in both in top.
What are the variables?
The constants.
Remember,
the constants.
Constants are not variables. Constants and variables are exactly opposite. If I ask you variables, you cannot give me constants.
I'm thinking of a placeholder, you know, like X, Y, Z.
Variables. What are variables? What are the variables here? What varies? Does M1 vary?
M1 doesn't change.
F1, V1, those don't vary. Those are not variables.
Okay.
This is a time invariant system. So X1 of S, X1 of S and X2 of S are the variables.
Those are the only variables.
F of S is also a variable. In the sense, it's not a variable in that sense. It's a known variable. It's something it's known, but it's a function of time. It's input, right? You're going to vary it, but you'll know how much you're going to vary. But this is something, so you can look at this and compare this to AX plus BY is equal to E CX plus BY is equal to F.
And that minus sign,
Hmm?
that minus sign.
This minus sign. So I've written. So what I've done is I've written x coefficients first
Okay.
and y coefficients next. So here there's a missing x2. Okay. So what you're trying to do here is, how do you solve this equation? What do you solve for? So here, what do you understand by this? What are the variables and what are the constants here?
Constants are A and B.
Right. A, B, C, D are constants.
Right.
X and Y are variables.
Right.
Okay. And these could also be variables. You can think about E and F as variables, or they could be constants. But they are known quantities. Okay. Now, what you're interested in is, see, if you were to develop this as a differential equation, you would get two differential equations. If you applied ODE or differential equations, that is the other way of solving the dynamics of this, right? And then what you would do, you would use some kind of solution to figure out what this x1 of t is or x2 of t. So here, what is this? If you look at this, this is algebra. Do you see any kind of calculus here?
No.
No, right? So this is, we have converted a calculation without really doing any kind of Laplace. This is actually the Laplace transform. We have indirectly applied the Laplace transform. Okay. Now this transfer function, I'll just introduce transfer function here. Okay. The ratio of output to input is called transfer function. So here, if I ask you, I'll ask you, question would be something like this. Find x1 of s over f of s, or x2 of s over f of s. Okay, so this x1 and x2 are output, right? This is output and f of s is input. There's only one input. Okay, so this is called the transfer function, the ratio of output to input. You understand why we do this?
No. This would be the ratio, that's right.
So if you know this f of s, you can figure out this x1 of s.
Okay, yeah.
So that is our goal, right? To figure out what this x, to seek a solution for x1 of output. You can seek a solution for x1 of s of x2. And if you take the inverse Laplace of x1 of s, what are you going to get? x1 of t, which is what you need. Okay. Now, how does this translate to control problem? Can you just think about how does this whole thing translate to, where is control here? Are we controlling anything?
I
What
guess
is
We're controlling
Here-
the force and the distance.
what is automatic control about this? You're studying your course is called automatic controls, automatic flight controls, right? So what is automatic? How would you make this automatic?
When you put your input in, the output does whatever you want
Right.
based on the
See,
input.
based on what kind of output you want, you will control your input. Your input will be controlled by, so you are not applying the force. If you want to keep on vibrating this, you have to know how much vibration you need, how much displacement you need. And accordingly, you can keep on controlling this force. Got it?
Yes, sir.
So that is the control. But to do that control, what you need is, you first need to understand the dynamics. You have to be able to derive the equations of motion or transfer function. Does it make sense, John Lewis? Quincy? Any doubts? Any questions?
Makes sense.
Cody? Alex? Make sense? For now? Tiffany? The other Tiffany?
Yeah.
Micah, dear Micah, does it make sense?
Why does she get a deal? And the rest of us just get.
But I'm there. I was put on the background. There you go.
I'll add it to the project.
Yeah.
I'll give it in the information. I have stability control 330.
Excellent.
Sounds like Thursday it is.
Huh?
Thursday.
We already said
Thursday
that.
would be okay. Thursday,
How come it's no
always
Thursday?
have 9:30 to 11. So, I mean, it depends
It's
on
50
everyone else.
minutes.
But it's a
Sorry.
You guys cannot give me 3 hours
Come up with another time.
in a week. You'll have to come on Saturdays then.
I said I'm down for 8 to 11.
Tell her you be the first one to talk about 8 o'clock. No,
Hey, I was on time this morning for 8.
8 to 11.